All right, continuing on in regards to our measures of central tendency as they relate to the standard normal distribution or the Z distribution, as well as variability in the data and our ability to draw inferences about the true population mean from a sample. So the question we've got here for you is, what impact does sample size, so how many people do you take measures from, have on standard deviation and or standard error, and also confidence intervals? So we're going to speak about confidence intervals here later as well. So what impact? Do you think it makes the standard deviation larger or smaller if you've got a lot of people in your study? So let's look. It's pretty easy. As you can imagine, it has a huge impact. Sample size has a huge impact, as does the variability in what is actually measured. So in order for us to get what's called standard error, we need the standard deviation, and we also need information about the sample or population size, in this case the sample size, little n. So how do you get this? Well, in order to get standard error, we need standard deviation, and as you remember, standard deviation is the sum of squares as it relates to some of these differences of individual samples from the median and the total population minus 1, the total population sampled minus 1, so the sample population minus 1. All of that goes into filling out the details about S, or the standard deviation, or sigma. So that gets in there. And then look what we got here. Standard error, standard deviation, and n again. So n is actually kind of buried into this equation twice, through both right here, which is all up there, and right here. So sample size has a very big impact on the standard error. It also has an impact on the standard deviation, as does the variability in whatever it is that might be getting measured. So there's a lot going on there in regards to the impact of sample size. As you would recall from earlier, from the previous video before this one, sample size can be already determined to be larger or smaller than standard deviation. So, I'm sorry, I'll repeat that. That was confusing. Standard error, how does it relate to standard deviation? So, which will be larger, the standard error or the standard deviation? So, whenever you take standard deviation and divide it by the square root of some number, we're going to find out that the standard error is going to be smaller. So, as we stated earlier, some folks will publish the standard errors instead of the standard deviations because it makes the averages plus or minus the standard error look like there's less error, when in fact it's irrelevant. They're both related so much. But standard errors, smaller numbers, usually you'll see them more common in the literature. In Stata, in order to actually get the standard error, you can just type in the command mean life expectancy 14. If you type in means, you'll get confidence intervals. You won't get just the standard error. You could do it by hand. So you could get your standard deviation, 2.38, divide it by your n value. So the standard deviation we had from earlier, it's right there, 2.38. And then 3135 is our n. So we had 3,135 observations here. So the standard error, in this case, determined to be 0.04 for life expectancy. Let's see how we get what we get in Stata. So if we were to pull up Stata and I was to do mean life expectancy, the standard error 0.0425. Let's go back to the PowerPoint, 0.0425. Continuing on with the PowerPoint. Standard error again is pretty easy to get, just mean. You will also periodically see folks use what's called the 95% confidence interval. Now, standard error is heavily related upon the standard deviation. So all of this is related around the actual intra-sample variability. So looking at the difference between individual measures of things like life expectancy for a county versus the actual sample population's average life expectancy. So it's the mean from within your sample. The confidence interval is the normal distribution. For the normal distribution, as depicted here, for a normal distribution here, we're going to use a z distribution. This distribution has this shape. Again, the t distribution will have different numbers, and it has kind of a smaller peak. So it's smaller than that, more flatter, not as sharp of a bell. But in the normal distribution, we had said earlier that 95% of the data would fit within 2 standard deviations. Remember this picture? Within 2 standard deviations. Well, that's because of rounding. In fact, 95% of the data fit between these two numbers, minus 1.96 standard deviations and 1.96 standard deviations. In fact, 97.5% of the observations are below this upper 1.96 standard deviation. So 97.5% of the observations are up here. So this assumes, how do they get these numbers? Well, there was this thing called the central limit theorem. It says that as you get large samples, if it's truly random and independent and behaves like a normally distributed data set, as it gets larger and larger and larger, 95% of the observations will fit between minus 1.96 and 1.96 standard deviations, with the true median, mean, and mode all being right here at the 0 standard deviation. Well, this is where your measure of central tendency will be. May seem a little confusing. It's always been confusing to me to a certain extent, but practical application of it is where you'll get more clarity. So in order to determine the 95% confidence interval of the mean, you could use this and do it by hand. So we use 1.96, so we say that the mean is plus or minus 1.96 the standard deviation over square root of n. All of this should look familiar. S over the square root of n, because S over the square root of n is also the standard error. So going back, the mean plus or minus 1.96 times the standard error. So that's all this right here. So we have our standard error. We calculated earlier to be 0.0425. We want the confidence interval, 95% confidence interval. It's 77.75 plus or minus 1.96 times the standard error. And then that will give us this number right here. And that means that we have 95% confidence that our mean is between these numbers. There's still a 5% window that the actual true mean could be outside of that window, but we're 95% confident that the true mean lies between here. Pretty tight confidence interval, between 77.67 and 77.83, when the true is 77.75. So that's the formula. Now this is, I rounded a lot, so we can do this in Stata. In Stata, we can use the command CI means life expect 14 variable x. You may also be able to use Stata and just type in mean life expect, as we see here, and that gives us the confidence interval of 77.67 to 77.835. The same numbers that we got when we did it here, except for this is 8.3 versus 8.35 due to rounding. Pretty easy to do, and we will continue on here in the next video in regards to doing some practical examples with some generated data so you can see how population size affects confidence intervals around the mean, as well as confidence intervals around other things like odds ratios and rate ratios. So that's enough for this video, and it will conclude here shortly in the next one.